The Michelson Morley experiment was designed to test the ether theory of light. The ether was imagined to be an invisible fluid dispersed throughout the entire universe, which transmitted light at a speed c equal 3 times 10 to the 8th meters per second. Just like water transmits water waves, and the air transmits sound waves. The experiment consisted of a source of photons, either light or laser, a beam splitter, and 2 mirrors B and C. The photons emitted from the source hit the beam splitter. Half of them would continue on to B and be reflected back. The other half would continue on to C and be reflected back. Now, because of the ether, it was expected that the time difference between the two legs would be different, and so if the Michelson-Morley experiment was rotated with respect to the ether, the fringe pattern observed when they came together would move. This just illustrates the Earth, the experiment on the surface of the Earth moving with velocity v through the ether due to the rotation around the Sun, and that velocity is approximately 3 times 10 to the 4th meters per second, and that's generally taken as the velocity for the experiment. But there's also an estimated universal velocity of the Earth through the ether of 5 times 10 to the 5th meters per second. Now, the experiment consisted in setting up the mirrors so that you observe a fringe when the experiment is in this position, which gives you a reference. Then when the experiment is rotating, now this leg and this leg experience different times, and the pattern was expected to shift. Now, the result of that experiment was that nothing happened. Now, the two ways of looking at the experiment are as follows. One is that the speed of light is constant with respect to source. That's also known as the ballistic theory, because the velocity of a bullet fired from a gun has a fixed velocity regardless of the velocity of the gun. It's always the same. Now, you can... and the other possibility was the speed of light was constant with respect to the ether. The best way, a way to illustrate these two, the difference between the two, is to think of the track from A to B as the track in a railroad car, with the frame fixed in the railroad car. And in this case, the photon is emitted with respect to at a speed c with respect to the railroad car. And that c from here to here is constant no matter how fast the railroad car is traveling. So that the time to travel each way is L over c, and the time difference is equal to 0, with assuming that in the vertical direction the same thing happens. You don't see the outside velocity of the vehicle. It's just the velocity with respect to the frame. Now, this result agrees with the Sagnac experiment, namely that the speed of light is constant with respect to source. Now, it agrees with the Sagnac experiment, and I've shown that in a video up till I did that calculation. The general argument was that it didn't agree. The general belief was that it didn't agree with Sagnac. That video is referenced in the title below. Now, the other expectation, or the other explanation, was that the speed, or assumption, was the speed of light was constant with respect to the ether. Now, that is the same as firing a photon or a bullet from the back of the car at some instant, and the instant the photon or the bullet, or just say photon now, the instant the photon leaves, is emitted, instead of having a speed c with respect to the vehicle or the back, it has a speed c with respect to the ground. In that case, the time it takes for the photon to travel back and forth depends on v. And the relative speed from A to B is c minus v, as seen from the car and in this direction, and c plus v in the opposite direction, so that the time to go back and forth in this direction is L over c minus v plus L over c plus v. And similarly, there's a different calculation for the vertical track of the photon after it's reflected. And the net result is, if you take the difference between those two, is that delta t is unequal to 0, and this has not been observed. This calculation for the vertical and the horizontal, I will do when I do the general case over here. Now the third explanation, which is that the theory of general, with the theory of specific theory of relativity, Einstein's theory of relativity, and I'm not going to cover it here because it's redundant, because Michelson Morley and Sagnac agree. Now, as I indicated here, I'm going to consider the general case for the Sagnac experiment oriented at some arbitrary angle with respect to the ether wind, or the velocity of the experiment v with respect to the ether here. This is fixed in the ether. This is a reference frame attached to the Michelson Morley experiment here. Now, I'm going to do a brief review of relative velocities, in case you're not familiar with it, where this now is the ether frame, fixed ether frame. This represents a frame any frame in the Michelson Morley experiment traveling at velocity v with respect to the ether frame E. And the photon is at some arbitrary position, rp with respect to the origin of the ether frame, and it has a position, its position is rp with respect to the moving frame, and where the moving frame is assumed to be traveling at constant velocity. That's important because I and j don't vary with respect to time. So now if you take the time derivative of this, you get the classic formula for the relation between relative velocities. Vp with respect to E is Vp with respect to A plus Va with respect to E. Now I note here, and this is very important, the velocity of P with respect to A is a straight line. In other words, when the photon is emitted at some arbitrary angle, it continues at that direction and comes, and if it hits a mirror, it returns to the same point. The reason is that if the path, for the ether theory, the path of the photon is a straight line in the ether, and since the Michelson Morley frame is moving at constant velocity with respect to the ether, which makes it an inertial reference frame, that straight line in E is also a straight line in the Michelson Morley experiment. So the photon comes back right to its starting point A. Now consider an arbitrary photon path Vp with respect to A that makes an angle alpha with respect to the ether wind V. And in that case, if I assume that the photon is traveling along that axis, then I can complete the frame with another axis perpendicular to it, and then I can apply this formula to give me that Vp with respect to A is equal to Vp with respect to E plus V minus Va with respect to E, which is plus Ve with respect to A. All right, now Vp, what we know here is we know the magnitude of the photon with respect to E. That's the velocity of the photon in the ether, and that's equal to c. And we know from here, we know the velocity of the ether with respect to A, the frame, and that's equal v. In other words, the frame is moving with velocity v through the ether. Then I can draw this vector relation as follows. I have the velocity of P with respect to A. That's in the direction shown here, angle alpha. Then I have the velocity of E with respect to A, which is in this direction from here to here. That's this. And I have that the velocity of P with respect to E is from here to here. The three are a closed vector form a closed vector diagram. This angle is alpha, this angle is pi minus alpha. And now, basically, the theory is finished. There's just algebra to do. From the law of cosines, this distance squared, which is c squared, is this distance, vp with respect to a squared, plus ve with respect to a squared, which is v squared, minus 2vpa, v cosine. This is alpha, this angle is pi minus alpha. So that's which can be solved for the velocity of p with respect to a for any angle alpha. Now, to take this situation here, where the x-axis is in the direction of v, alpha is equal to 0, and that's from a to b, from b to a, alpha is equal to pi, and that gives me velocity of p with respect to a as c minus v and c plus v. For the direction going up and coming back down, alpha is pi over 2 and 3 pi over 2, from which the velocity of p with respect to a is c squared c squared minus v squared. Then, finally, the difference in time between the two paths, which creates the fringe, is delta t, is t vertical minus t horizontal. The vertical time is the distance, 2L, divided by the vertical speed, which is the square root of c squared minus v squared. And the horizontal time is L over c minus v, which we had here, plus L over c plus v. And that, if you do if you work through the algebra and make some simplifications, that works out to be L v squared over c times c squared. Now, that's the time offset. To get the distance offset, that's equal to the vertical velocity times the time delta t, and the vertical velocity we had was the square root of c squared minus v squared, which you can write as c times 1 minus v squared over c squared, and 1 minus v squared over c squared can be 1 over the square root of 1 minus, the square root of 1 minus v squared over c squared can be calculated from this approximation from Taylor's expansion. This is equal to 1 minus x over 2, and you ignore the higher order term in v over c to get that, and you get that this is just c times this term here, or lv squared over c squared. Now, these two results are also given in the wiki article on Michelson Morley Experiment, but this method is not used. It's calculated with respect to the calculations are done with respect to the ether frame, in which case they use the water analogy of a boat trying to cross a stream, and it's going to go across at an angle. I never really felt comfortable with that. That's why I did this. This explains clearly what reference frames you're using. I just add a note here. In this calculation, I use some algebraic simplifications from Taylor's series. Taylor explained 1 over the square of 1 minus x is 1 plus, approximately 1 plus x over 2. Square of 1 minus x is approximately 1 minus x over 2. And 1 over 1 minus x is approximately 1 plus x. Now, finally, I note that this is not an academic calculation, because if you get a 0 result, it's quite possible you got that result because your apparatus was not sensitive enough to detect the difference in the due to the orientation of the experiment. However, it was calculated that, what was determined, that the Michelson Morley experiment was sensitive enough to determine any difference of this order of magnitude. So finally, what we're left with is that the Michelson Morley experiment and the Sagnac experiment both have exactly the same result, that the speed of light is constant with respect to source, which is the ballistic theory. Now, as I mentioned before, I've calculated the Sagnac experiment result in a YouTube video, and I've given a reference which you can get by tapping on the title of this video. Thank you.